series. This series is designed for those crucial final days before your interview, when you need fast, sharp revision rather than a long theory. We focus on exactly what matters, the core concept, the right terminology, and how to present each topic in a way that makes the interview feel confident about your understanding. Our goal is simple: quick clarity, strong fundamentals, and interview ready explanation without any unnecessary academic fluff. So let's dive in and sharpen your microservice knowledge for the big day. Thank you. Let's see what we will be covering in this session. We will begin with the fundamentals of OAuth and how modern system manages secure authorization. Then we will look at the CQRS patterns and why separating reads and writes benefits performance in the microservices. We will move into the security practices, including the rate limiting and other measures that keep the distributed system protected. From there, we will explore event-driven architecture and the importance of the idempotency when dealing with the retries and message processing. Next, we will look at the database sharding and broader techniques for managing the data consistency across the services. We will also discuss the Canary deployments, a safe approach for rolling out a new features in a production. Monitoring is essential, so we will talk about effective way to observe and troubleshoot the microservices. Then we will touch on DDD principles, scalability strategies, and the role of sidecars in a service mesh. We will wrap up with the production development best practices, key design practices, and simple end-to-end flow that brings all these concepts together. By the end, you will have a clear picture of how build secure, scalable, and resilient microservice architecture. In this slide, we will talk about OAuth, something we use all the time, even if we don't realize it. OAuth, or Open Authorization, is basically a secure way for one service to access a user's data from another service without even touching their password. Instead of sharing credential, OAuth uses access token, which act like a temporary permission slips. And the key idea is that OAuth cleanly separates authentication, that means who you are, from authorization, means what you are allowed to access. This makes everything safer and much easier to manage. Now see, why do we use OAuth? We use OAuth because it allows safe control access. An app can access your data, like your name or email, without even seeing your password. User also get fine-grained control. We call it as a granular access or scopes. For example, you can allow an app to read your contacts but not send emails. OAuth tokens are short-lived and recoverable, which boosts the security. And because it's perfect for the third-party integration, platforms like Google, Facebook, and GitHub, and so many rely heavily on the OAuth. This is now industry common practices to use the OAuth in microservices to get certain access without registering in the app directly. Now let's see a real world example. You have definitely seen this. Log in with Google. You click the button, Google authenticates you, and then share the token with the app. The app uses that token to access only what you allowed, like your name or profile picture. But it never ever see your Google password. So, in short, OAuth gives you a secure, selective access without giving away the key to whole the house. Let's talk about a pattern that really shines in a large-scale microservices, and that is the CQRS. It stands for Command Query Responsibility Segregation. But don't let the name scare you. This idea is actually very simple and powerful. CQRS says, let's stop treating reads and writes the same way. On one side, we have the command model. This handles all the heavy duty work like creating, updating, and deleting data. On the other side, we have the query model. This is focused on reading data as fast and efficiently as possible. By separating these two responsibilities, each side can evolve and scale independently. You can tune up your write side for a consistency and business rules, and tune your read side for pure speed and optimization queries. What problem does CQRS solve? Because it solves several headaches as your system grows. First, tackling performance bottleneck. Read and writes behave very differently under loads. With CQRS, we can scale the read sides separately. Perfect when thousands of users are constantly querying the data. Second, simplifying complex read queries. When the same model handles both read and writes, read queries get overly complicated. CQRS gives you a clean, dedicated read model that's designed purely for fast data reading or fetching. Third, reducing coupling in domain logic. In traditional CRUD system, read and write logic often end up tangled together. A CQRS cleanly separates them, making the code base easier to maintain and evolve. Fourth, keeping reads fast even under a heavy writes. Since reads and write happen on a different paths, read don't get stuck behind the write locks. That means user experience constantly fast response even when the system is handling a flood of writes. Fifth, choosing the best storage take for the each side. One size doesn't fit all. So CQRS gives us the freedom to pick up the right storage for each workload. Strong consistency for commands, high speed querying for reads. 6. More efficient scaling. Instead of scaling one monolithic database, we scale what we actually need. That is a read or write. That makes scaling both cheaper and far more effective. So overall, CQRS helps us building system that stays fast, flexible, and scalable even as complexity grows. In this slide, we will discuss about security in the microservices, how we protect both the APIs and internal communication. First, the API gateway, it acts as the system front door. Every request passes through it where we enforce authentication, authorization, rate limits, and IP filtering. Only legitimate traffic gets in. We rely on a token-based authentication like OAuth or JWT instead of a password. Token securely represents identity and permission for every call. For internal service-to-service communication, we use mutual TLS. This ensures encrypted channels and that only verified services can talk to each other. A role-based access control, that is RBAC, with scopes, gives fine-grained authorization. Service and users only get the access they truly need and reducing the risk. We reinforce APIs with best practices like strict input validation, throttling, and rate limiting to protect against DDoS, brute force, and injection attacks. All sensitive data is encrypted both at rest using like AES or KMS algorithm or in transit like HTTPS or TLS, keeping it safe from the hacker sites. Our system follows a zero trust model. No service is automatically trusted and every request must authenticate and authorize itself. Secrets like credentials are never hard-coded. They are centrally stored and rotated using tools like Vault, AWS Secret Manager, or Kubernetes Secrets. For container security, we scan images for vulnerabilities, use a minimal and sign-based images, and enforce restricted permissions. Finally, monitoring, logging, and auditing with ELK, Prometheus, and Grafana help us detect anomalies early and investigate incidents effectively. A great example is Netflix. They use OAuth and JWT for user identity and mutual TLS for internal service communication, strict rate limiting at the API gateway, and central secret management. Everything is encrypted end to end, and their monitoring stacks catches issue before customer even notice. So, in short, strong layered security isn't optional. It's essential for keeping microservices resilient and trustworthy. In this slide, we will discuss about the rate limiting. It is basically the traffic control system of microservices. It decides how many requests a client can send in a specific time window, so the system doesn't get overloaded. Why we use it? It protects the service from the spikes, abuse, DDoS attacks, or accidental overload, and it makes sure every client gets a fair access instead of one user blocking everything. How it works? We can apply a limits per user, per API key, per IP, or even per microservices, whatever level of controls we need. When it is enforced, most of the time the API gateway like Nginx or AWS API gateway handles the rate limiting before traffic reaches your services. How it is implemented? We use algorithms like token bucket or leaky bucket to control the flow. In distributed system, the tools like Redis help to keep the track of global limits consistent across all the service instances. What happens when the limit hits? The client gets a 429 HTTP code. That is a too many requests plus a retry after hint, telling them when to come back. Let's see one real example. One of the best example is Twitter. They enforces limits like 300 tweets in a 3 hours per user. Their API gateway tracks each user's activity, and if someone crosses their quota, it immediately sends a 429 response. This keeps the platform safe from abuse, ensure fairness, and still gives the genuine users a smooth experience. Alright, let's talk about one of the most powerful pattern in the microservices, and that is the event-driven architecture or EDA. I will use the EDA short form for the event-driven architecture throughout this slide. So let's see what EDA really is. The EDA architecture is all about letting services talk through event instead of a direct API calls. So instead of one service calling another and waiting for a response, it just shouts out, "Hey, something happened," and whoever cares can react. This creates a completely asynchronous and super scalable communication model. What exactly is an event? An event is simply a meaningful change in the system, something that's worth telling others about. It could be a order placed, payment completed, or driver assigned. Think of an event as tiny announcement that other services can choose to act upon. The three main players in the EDA. In an event-driven system, we usually have three main actors. Event producer, these are the one raising the announcement. For example, the order service emits an order place event. Second, the event consumers. There are services that listen and react. For example, inventory reduce stocks and notification sends an SMS, etc. Third, event brokers, the middleman that routes events reliably. Tools like Kafka, RabbitMQ, or AWS SNS or SQS make sure events get where they need to go. Event at a massive scale. How the communication works. The magic of EDA is that everything is asynchronous. The producer doesn't care who listens, how many services respond, or how long they take. It just emits an event and move on. This decoupling is what makes the microservices much more flexible and scalable. Why EDA is so powerful? This approach gives us a ton of benefits. Service stay loosely coupled. Second, the system becomes easier to scale independently. The failures are more isolated. We can react to things in a real time, and the whole architecture becomes more resilient and responsive. But there are some challenges too. Of course, nothing comes for free. With EDA, debugging can feel like a chasing events across the universe. You haven't you have to think about event ordering, consistency across services, and making sure messages aren't lost. Strong persistent retries and observability becomes crucial. So let's see one real world example. That is a food delivery app. Let me give you a real relatable example. Think of a food delivery pattern. When the order service publish an order place event, the restaurant service instantly starts and preparing the food. The delivery service pick the rider. The notification service send a confirmation to the customer. And here is the cool part. None of these services talk directly to each other. They simply react to the same events in their own way. That's the power of event-driven architecture. That is independent scaling, zero tight coupling, and a system that stays resilient even under a heavy load. Let's talk about something that quietly keeps distributed system from falling apart, and that is the idempotency. It sounds like a big word, but the idea is actually simple and incredibly powerful. What idempotency really means? Idempotency basically means even if you perform the same operation multiple times, the final result stays the same. So, whether a request runs once, twice, or 10 times, your system ends up in the same state. No duplicates, no corrupted data, no surprise. This is the essential in APIs, databases, and anywhere repeated calls might happen. And trust me, Repeated call happens a lot in the microservices. Why idempotency matters in the microservices? In microservices, services are constantly talking over unreliable network. Call fails, service retry, clients retry, message brokers recent events, and without idempotency, retries can cause serious chaos. Imagine duplicate orders, double payments, inventory being deducted twice, events being processed multiple times. Idempotency prevents all of this. It also plays a big role in event-driven system, where the same event may be delivered more than once, which idempotent consumers. We can process events safely, no matter how many duplicate arrives. And when we combine idempotency with retries, circuit breakers, queues, or backup strategies, the whole system becomes far more reliable and fault tolerant. Let's see a real world example. Let me give you example of payments. A user clicks pay. The network drops for a moment. The app retries the request. Without idempotency, the user could get a charge twice. But with an idempotency key, the payment service says, "Oh, I have seen this request before. Return the same result and don't change a charge again." Another example is HTTP method. Get is a natural idempotent. You can fetch something 100 times, nothing changes. Put is idempotent too. Updating your resources to the same value keep the state identical. Post, however, is not an idempotent. That's why we often wrap post operation like order creation in idempotency keys as well. So here is the big takeaway. The big picture is simple. Idempotency is one of the foundation of reliability in distributed system. It lets handle retries smoothly, prevent duplicate action, protect our data, and keep the system stable, even when the network is not there. In short, idempotency makes microservices safe. Let's talk about the database sharding, one of the most powerful techniques for scaling the data in microservices world. Imagine your database is huge library. If all the books are piled on one shelf, it's slow, crowded, and eventually impossible to manage. Sharding solves that by splitting the library into multiple smaller rooms, each holding a portion of the books. That's the exactly what sharding does with data. It breaks one large database into the smaller independent pieces called shards. What exactly is database sharding? Sharding simply means taking a large dataset and splitting it into a smaller manageable chunks. Each shard lives on its own database, several servers, and store the data based on a sharding key. For example, user ID, region, or customer ID. So instead of one giant database doing all the works, we have multiple smaller databases working in parallel. Why do we use sharding in microservices? First, scalability. Sharding lets us scale horizontally by spreading the load across many servers. No more single database bottleneck. Second, better performance. Since each shard handles a smaller dataset, queries run faster and latency drops drastically. Third, isolation of workload. A big report or heavy traffic hitting one shard doesn't affect the others. Everyone else stays fast and responsive. Fourth, high availability and fault isolation. If one shard goes down, the rest of the system continues working normally. Failure stays contained. Fifth, perfect fit for microservices. Microservices loves decentralization of data, and sharding supports exactly that. Each service can own the shards or partition relevant to its domain. 6. Multi-tenant and global support. Sharding by tenant or region is a great for global apps. Users in India can hit data stored closer to them, reducing latency and improving experience. The real world example. Suppose the e-commerce platform. Think of an that e-commerce system. User IDs might be split like user 1 to 1000 in a shard 1, then user 1001 to 2000 in a shard 2. So when a user places an order, the system only touches the shards that holds their data. That means faster lookups, smoother scaling, and better failure isolation. Twitter also uses sharding. With billion of tweets, they split data often by user ID or tweet ID, so the load spreads evenly across many servers. So final takeaway is that Database sharding breaks a massive data sets into a smaller, faster, and more reliable pieces, making your microservices scalable, resilient, and high performing. When we move from a monolithic to microservices, one of the first challenge we hit is a data consistency. In a monolithic, one database keeps everything simple, but in a microservices, every service owns its own data and communicate over the network. That changes the game entirely. Independent data in a distributed world. Each service has its own database, logic, and scaling behavior. Traditional ACID transactions across services are not possible. So we need a smarter strategy to keep the data reliable. Even if it's not immediately consistent, we need to consider CAP or Passel theorem. Then event-driven architecture. Let's events do the talking. The best way to connect the services is an event. Service communicate asynchronously via tools like Kafka or RabbitMQ. For example, an order services publishes order place, inventory updates the stock, payment charges the customer, everyone stays decoupled, scalable, and resilient. Then saga pattern, breaking the transaction into the steps. We manage multi-steps workload using sagas. There are again two parts, choreography and orchestration. In choreography, each service triggers the next like a relay race, and in orchestration, a central coordinator guides the process like a conductor. Saga helps us achieve eventual consistency without freezing the system. Then, idempotency. In a distributed system, retries happen, crash, duplicates timeouts, you name it. Uh, Operations must be idempotent. Retrying the same action shouldn't break anything. A payment request, for example, shouldn't charge the customer twice. Then eventual consistency. Data won't always be perfectly in sync. That's okay. The system can tolerate brief staleness and still cover to a correct state. Accepting this delay makes your system much more resilient. Then distributed logs. Sometimes you really needed to prevent conflicts. Distributed logs via Redis or Zookeeper can help, but they add complexity and bottleneck. Only use when the absolutely necessary. Then compensation. When a step fails, we compensate rather than the rollback. Example, payment successful, but inventory fails. Issue a refund automatically. The system stays consistent and user stays happy. Database level patterns. We also leverage CDC, that is the change data capture, turns database changes into an event. Event sourcing stores every state changes as an event to rebuild service state anytime. This tool keeps service aligned without the tight coupling. The real world example, that is the e-commerce flow. An online order. Order service creates it. Publishes order place. Inventory receives stocks. Payment charges the customer. If something fails, compensation like order cancel kicks in. Eventually, all services settle into a consistent state. No locks, no global transaction, just reliable and coordination. So key takeaways, event-driven design, saga idempotency, compensation, and eventually consistency. These are what makes a distributed data reliable. Strong consistency is rare. Resilience is the real goal. So in microservices, it is not about perfect sync, but it's about building a system that stays correct even when the world gets messy. Let's talk about one of the safest and smartest way to release a new features into the production, and that is the canary deployment. Think of this like introducing a new changes quietly to just a small group of users first, almost like sending a canary into a coal mine to check if environment is safe. Instead of pushing the new version to everyone at once, we let tiny segment experience it, observe what happens, and then slowly widen the rollout. What is canary deployment? Canary deployment is a gradual rollout strategy. We release the new version to a small percentage of users, maybe 5% or 10%, while everyone else stay with the stable version. It lets us test real production behavior with minimal risk. Why do we use it? The main goal here is early detection. If the new version has a bug, performance drops, or even hidden edge case failures, only a small portion of the users are affected. This dramatically reduces the risk of breaking the entire system. How Canary deployment works. First, release to a small user segment. We start by routing a small slice of traffic to the new version, usually just a few percent. It's like dipping one foot into the water instead of jumping straight in it. Then monitoring everything closely. As that small traffic flows in, we watch the metrics like how it works, error rates, latency, resource uses. This is where we validate whether the new build behaves the way that we expected. Then slowly traffic increases. If everything looks good, we expected the audience maybe 10%, then 25%, then 50%, and all the way to the 100%. Each step builds confidence. Then roll back instantly if needed. And the beauty is if something goes wrong at any point, we instantly revert back to the old version. Users won't even notice it. Then powered by automation. This whole flow is typically automated using a tools like Kubernetes, Istio, or Spinker and integrated right inside the CI/CD pipelines. That's what makes Canary release fast, predictable, and safe. Canary deployment gives us several major advantages. Much slower risk when rolling out a new version, real-world testing without exposing everyone, and instant rollback if issue shows up. And they fit perfectly into a continuous delivery and DevOps pipelines. It's one of the most reliable way to deliver features at a high speed without losing the sleep. So Canary deployment ensures we innovate quickly while keeping our users safe. Small steps that led to a big confidence. Let's talk about observability in a microservices. Basically, how we see what happens inside a distributed system. Centralized logging. Centralized logging gives us a single source of truth for all our logs. Instead of chasing log files across different services, everything lands in a platform like ELK or Splunk, making troubleshooting and auditing so much easier. Then second, metric collection. We track key matrices like latency, throughput, error rates, CPU, and memory. With tools like Prometheus and Grafana, we can spot performance issue before they hit the users. Third, distributed tracing. Distributed tracing follows a request step by step across the services. Tools like Zipkin help us quickly find bottleneck or failure in a complex flow. Then health checks. Health checks acts like a doctor visitor for a services. Kubernetes or load balancer use the liveness and readiness endpoints to route traffic only to healthy instances and auto heal the sick ones. Fifth, alert and notification. We set alerts on things like latency spikes or error rates so the team gets notified before a small issue becomes a major outage. Then service level monitoring. We track each microservice individually, uptime, requests, errors, so we know exactly which service is causing trouble instead of guessing. Point 7. End-to-end monitoring. Synthetic monitoring simulates a real user's journey. It's like sending a test user through the system to catch problems early. Then dashboarding. Dashboarding pulls metrics, logs, and traces into a one real-time view so team can instantly understand what's going on. Together, these practices gives a true visibility, so we can detect issue early, fix them fast, and keep our system reliable. Let's look at how domain-driven design, that is DDD, help us building microservices with a real clarity and purpose. Focus on the domain. We start by shaping services around actual business domains, not technical layers. This keep each microservices aligned with how the business truly works. Then bounded context. Each service becomes its own little world with its own rules and its own model and its own data. This reduces confusion and keeps services cleanly separated. Then entities and value objects. Entities represent things that have identity over a time, like an order or a user. Value objects are simpler and immutable, like an address or money. They describe what something is not and who it is. Then aggregates. Within each service, related entities are grouped into aggregates with a clear root. The root enforces consistency and ensures the rules are followed. Then domain events. When something important happens, like an order being placed, we publish a domain event. Other services can react independently, creating a smooth event-driven flow. Repositories. Each service manages its own repository and database. This keeps data ownership clean and support true microservices autonomy. Then ubiquitous languages. We use one shared language across business and code. When everyone speaks the same terms, misunderstanding disappears. Then anti-corruption layers. And when we integrated with a legacy system, the ACL acts as a translator. It protects our domain model so external systems don't pollute it. A real example is e-commerce platform. The order service owns everything about the orders. The inventory system lives in its own context and simply reacts when it hears order place. Separate models, separate data, and clean boundaries. So DDD helps microservices stay focused, independent, and aligned with the businesses. Exactly what a scalable system needs. Let's talk about one of the biggest goals in a microservice architecture, and that is the scalability. Not just scaling one component, but scaling the entire system intelligently and efficiently. Service decomposition. Start by breaking things apart. Scalability really begins with how we break the system down. When each service is focused on one business capability, it can grow on its own without pulling the rest of the system with it. That's the foundation of a scaling smart. Then stateless services, the secret to easy replication. Whenever possible, we keep services stateless. That means no storing session data inside a service itself. Push it off to Redis or similar store. Stateless service can be cloned effortlessly, which makes scaling almost plug and play. Horizontal scaling, just add one more instances. Need to handle more traffic. Instead of beefing up one machine, we simply run more copies of our services. Platforms like Kubernetes, ECS do the heavy lifting, spreading instances across nodes and balancing traffic automatically. Database scalability. Avoid a single bottleneck. Every service should own its data, and that open the door to scaling the database in the right way. Sharding, partitioning, read replicas, or NoSQL databases helps manage heavy read-write workloads without choking the system. Asynchronous communication. Don't let the service wait around. One of the biggest wins for scalability is going asynchronous. Using queues or event streams allows services to communicate without blocking each other. This removes pressure from the synchronous APIs and massively boosts throughput. Then caching, your fast lane for performance. We also rely heavily on caching. Storing frequent access data in a Redis or Memcached reduces the database loads and gives us the lightning fast responses. It's one of the simplest but most powerful tools scaling. Then auto-scaling and orchestration. It scales automatically, not manually. With Kubernetes or cloud auto-scaling, the system grows and shrinks on its own. During the peak hours, it scales up, and during the quiet times, it scales down. That means we stay responsive and cost efficient. Then API rate limiting and throttling, protecting the system under the stress. Traffic spikes happens sometimes unexpectedly. Rate limiting and throttling keeps services safe for preventing overloaded. Instead of crashing the system, gracefully handle all the issues. Then partitioning or multi-tenancy, distributed the load smartly. Another way to scale is by splitting users or data across shards or partitions. This spreads the load so no single part of the system is overwhelmed. It's especially powerful for a large multi-tenant platform. Then monitoring and metrics. Scale before problem occurs. And one, of course, we don't wait for an issue to hit users. Constantly monitoring CPU, memory latency, and request rates helps identify bottleneck early. Good metric later scale proactively, not reactively. Let's see a real world example of Netflix. A great example. They use all of these techniques, stateless services, massive horizontal scaling, Kafka for events, Redis caching, and Kubernetes also scaling. And that's why millions of people can stream non-stop without noticing any of the complexity happening behind the scenes. Scalability isn't a single feature. It's a mindset that has to be worn into every layer of the architecture. Alright, let's talk about one of the coolest design pattern in the microservices world, and that is the sidecar pattern. If you are imagining your microservices as a motorcycle, the sidecar is the extra attachment riding right beside it, supporting it, but never getting in the way. What is a sidecar? A sidecar is basically a companion container or a process that runs right next to your main services. It's like ha- it's like having a dedicated helper whose job is to handle all the extra stuffs, while your main service stays focused purely on business logic. Why do we use it? What makes the sidecar so useful is that it handles all those cross-cutting concerns we don't want to bake into every services. Things like logging, monitoring, security, configuration, networking, all the messy infrastructure works live in the sidecar, and the main service remains clean and simple. How it is deployed? In practice, the sidecar is deployed as a separate container in the same pod, especially in Kubernetes, or sometimes as a parallel process. They sit side by side, communicate seamlessly, and operate independently. Your main service doesn't even know the sidecar exists, it just benefits from it. Key benefits. This setup gives us a lot of power. We cleanly decouple infrastructure concerns from the core logic. Observability becomes a bridge. Sidecars collects metrics, logs, and traces. They can add reliability features like retries and circuit breakers. And updating the capabilities is easy. You update the sidecar, not the main app. It is a modular and clean, incredibly flexible. A real world example. You see sidecars everywhere, especially in the service meshes. For example, EY in ISO works exactly like a sidecar, handling traffic, security, and routing for each microservices. Sidecars also collect the logs, manages configurations, store tokens, and gradually uh, and generally act as the infrastructure Swiss Army knife. At the end of the day, sidecars lets team build microservices that are focused, maintainable, and scalable, while all the heavy lifting happens right in beside them. Alright, now let's talk about what really matters when you move microservices into the production. Because designing microservices is one thing, but running them reliably at a scale is a whole different game. Containerization and orchestration. Your deployment foundation. We always start by containerizing our services with a Docker. That gives us a consistent, predictable builds every single time. Then we had those containers to orchestrate like Kubernetes, which takes care of scaling, scheduling, and keeping everything running smoothly. It is the backbone of stable production environment. Then CI/CD pipelines. To avoid slow error-prone releases, we rely on CI/CD pipelines. Tools like Jenkins, GitHub Actions, and GitLab. CI/CD automate building, testing, and deployment. This keeps delivery fast, repeatable, and safe. No manual deployment nightmare. Service discovery and load balancing. In microservices, services are constantly scaling up, scaling down, and moving around. So instead of hard coding, we use the dynamic service discovery and smart load balancing. This ensures traffic always flow to healthy instances without the manual updates. Observability. To keep production system healthy, we need full observability. That means collecting logs, metrics, traces with tools like Prometheus, Grafana, EK, and Jagger. When something breaks at 2 a.m., these tools helps us find and fix it instantly. Resilience and fault tolerance. In a microservices, failures are normal, so we add patterns like circuit breakers, retries, bulkhead, and rate limiting to prevent small issues from becoming a system-wide outage. Then configuration management. We keep configuration outside our code using a config maps, secrets, or service registration. This way, we can tweak setting for different environments, dev, test, pod, without redeploying anything. Security. Security isn't optional. We use API gateway, enforces authentication, manage secrets properly, and apply mutual TLS between the services. This keeps unauthorized access out and protects sensitive data. Versioning, backend compatibility. When users evolve, we use proper API versioning to keep older clients working. This allows teams to upgrade safely without breaking anything downstream. Scalability and resource management. We design service to be stateless whenever possible, so they scale effortlessly. Then we set a resource limit and let Kubernetes auto-scale based on traffic. This ensures we scale intelligently and avoid wasting resources. Then blue, green, and canary deployment. To reduce deployment risk, we use strategies like blue, green, and canary releases. They let us roll out new version gradually, test them with the real traffic, and roll out instantly if needed, all with a zero downtime. So in short, deploying microservices in production is not just about running the services. It's about building a system that automates, observable, resilient, and ready for anything. Alright, let's walk through some of the most important design patterns that makes microservices actually work in the real world. These patterns helps us building systems that are scalable, maintainable, and resilient, especially when things get messy across a distributed service. So here I'm just list out the design patterns that are useful. First, API gateway, that is the front door of your system. Second, Saga pattern. It is handling the transaction across multiple services, and we can do it in two ways. One is choreography, that is a service trigger each other using the events, and second, orchestration. A central controller tells each service what to do next. Then CQRS, separating reads and writes. Fourth one, event sourcing, storing the changes as an events. Instead of storing just the final state, event sourcing stores every state changes event. Then database per services, that is the independence at the data layer. In microservices, each service is own its own database. This keeps services decoupled and lets them scale or evolve independently without stepping on each other's data. Then strangler free, evolving from monolithic to microservices. This is my favorite migration pattern. You don't rewrite the entire monolithic in one shot. You peel off features into microservices one by one, and slowly the monolithic shrinks until it disappears. Then circuit breaker, it preventing the cascading failures. When a service keeps failing, we stop calling it and use a fallback instead. This protects the entire system from collapsing because of one bad dependency. Then bulkhead pattern, containing the failures. The bulkhead pattern isolates resources like thread or connection pools. So if one service gets overloaded, it can't take the down the rest. It's like putting what yeah, it's like then let's take the next pattern, that is a sidecar pattern. Helper containers for extra tasks. In many architecture, we attach a sidecar container that handles logging, monitoring, networking, or security. The main service keeps its code clean and the sidecar takes care of the supporting work. Then retry and timeout, the smart handling of our temporary failures. Then next, service discovery, finding the service dynamically. Services don't use hard-coded URLs. Instead, they register themselves and other discovers them dynamically through the tools like Eureka, Consul, or Kubernetes. Then adapter or anti-corruption layer, protecting microservices from legacy chaos. Together, these patterns from the toolbox that lets microservices stay organized, reliable, and ready to scale, no matter how big the system grows. Let's walk through how microservice system works end to end, and we will use a simple example, a user placing an order. The client requests, the journey begins, a user taps place order on the app. That one action kicks off the entire microservice workflow. Then API gateway, the smart front door. Before anything reaches the backend, it hits the API gateway. It handles authentication, routing, rate limits, logs, and then forward the request to the right services, like the order service. Order service takes over. Now the order service pick up the request and run the business logic. It doesn't work alone. It coordinates with the other microservices to finish the job. Then service communicate to complete the workflow. To place an order, the order service might check the stock through inventory, process payment through the payment service, trigger notification through the notification service. These calls can be real time, either it is a REST call or gRPC, or even event driven like Kafka or RabbitMQ. Then each service has its own database. Every microservice stores its own data, order DB, inventory DB, payment DB. This keeps them independently and scalable. Then asynchronous events in the background. Some tasks don't need to block the main flow. So the order service might publish events like order place, and service like notification or shipping pick them up when they are ready. Then service discovery and load balancing. Behind the scene, service registry themselves in a registry like Eureka or console. Load balancer then route the traffic to healthy services instances. Then service mesh magic, that is Istio or Envoy. A service mesh quietly handles retries, circuit breaking, encryption, and observability. So developers can focus on features, not networking. Then centralize observability. All logs go to ELK, metrics to Prometheus, and tests to Jagger. This gives us a clean picture of everything happening across the dozen of services. So final response to the user. Once everything is done, payment confirmed, stocks validated, the API gateway sends the final response back to the order confirm. A short real world example is like user place an order, then it goes to the API gateway. From API gateway it goes to the order service. Order service checks the inventory in the and then process the payments. Order service save order, publishes order place event. Notification service sends an email and SMS. Shipping services schedules delivery. API gateway returns order confirm. And that's the power of microservices. Multiple small services working independently yet coming together seamlessly to deliver a smooth end-to-end experience. That's about in this video.